Hello, welcome to Advanced Composites. Today is the fourth day of the ongoing 11th week of this course. Yesterday we had started developing the solution for buckling of an infinitely long plate which was having a width of b meters, and we had developed the following equation. What we had also done was that we had assumed a displacement function for w, mid plane displacement out of plane in the out of plane direction, and we had seen that if I use this kind of a function, then this function satisfies all the boundary conditions associated with the infinitely long simply supported plate. And then the next step was to somehow ensure and explore whether this function also satisfies the boundary conditions. So, what we will do is that in this modified differential equation, we will plug in the value or the function for w naught and see what it implies. So, now what we do is w naught x y is equal to w naught sin pi x over lambda sin pi y over b, and lambda is a parameter and we will interpret what that lambda is. B is the physical dimension of the plate, it is b meters wide. So, if I plug in what so this is equation A, this is B. So, we put B in A. So, what do we get? We get minus n, and this is differentiated twice in x, the first term. So, it becomes pi square over lambda square plus d11 pi over lambda to the power of 4 plus 2 d12 plus 2 d66 pi to the power of 4 over lambda square b square plus d22 pi over b to the power of 4 w naught sin pi x over lambda sin pi y over b, and this equals 0. So, this is the equation, and this equation we are getting. So, this is equal to 0. This equation we are getting from the PDE, from the partial differential equation. So, this equation should be valid at all times. It should be valid at all times for all values of x and for all values of y. Now, this is true only in two conditions. So, what I will do is I will put this thing in green brackets. So, only this is valid in two situations. What are the two situations? One is w naught is equal to 0. Okay. If w naught is equal to 0, which means that I have a perfectly flat plate and it is in an ideal situation, it does not experience any ideal disturbances, it is homogeneous, it is perfectly symmetric, all the conditions which we had described way back in the beginning of this week. And then if I keep on pressing it using externally compression load, then it will never buckle. Okay. If it is perfectly flat and it does not get any disturbances, and if it is perfectly homogeneous and it is the lamination sequence is perfectly symmetric and so on and so forth, and the loading is also perfectly at the mid plane, it is not slightly off center. So, that is this thing, because this w naught is here. So, if w naught is 0, then it will never buckle. Or So, this is one condition, or this term in green brackets, this becomes 0, and that condition corresponds to the buckling phenomena. So, either W is 0 or W can be non-zero, but the term in the green brackets, that has to be 0. So, this term in the green brackets relates to buckling phenomena. Okay. So, when is it 0? So, let us write down. So, if this thing in green in the green brackets, this is equal to 0, then it implies that n pi square over lambda square is equal to d11 pi by 4, I am sorry, pi over lambda to the power of 4 plus 2 d12 plus 2 d66 pi 4 over lambda square b square plus d22 pi over b to the power of 4. Okay. So, if this condition is 0, if this condition is satisfied, then the term in the parenthesis is 0. Or what I can do is, I can remove this thing and I can multiply this entire thing by lambda square by pi square, and this pi. Okay. So, that is my critical. So, corresponding to given lambda, n can be found. What does that mean? That if, so what is W sin pi x over lambda sin pi y over b? What does it mean? That this tube, this plate is there, which is infinitely long, and the deflection pattern in this direction, in the x direction, is like this, and so this is lambda. This is lambda. This is the wavelength of the buckling pattern in the x direction. Similarly, the wavelength in the y direction is b, or actually it is half wavelength, because what is the full wavelength? Full wavelength will be like this. So, this is b. So, half wavelength in the y direction is b, and in the x direction it is, actually this is 2 lambda. Okay. So, that is there. So, corresponding to any lambda I can calculate an n. So, what that means is that the plate, you keep on loading it, and after some time it will buckle, and as I keep on increasing the load, wavelength will keep on changing. Okay. And this change will keep on happening continuously. It will not happen at discrete values. So, it will keep on happening continuously. So, as I keep on increasing the load, this lambda will become, as I increase n, what will happen to lambda? Lambda will become smaller. So, essentially what that means is that if I keep on pressing it, this wavelength keeps on becoming smaller and smaller. Wavelength keeps on becoming smaller and smaller. So, that is what it means, and this change will happen continuously. Okay. So, this is what it means. Another way to look at it is that if I want to know that associated with a lambda there is a value of n, another question is that suppose I impose on it some value of n, then corresponding to that value of n, what will be the value of lambda? So, this is the other question. that for a given n, what is lambda? So, that also we can solve this equation and we can find it out, because this is an equation which is having terms in lambda 4, lambda square and lambda to the power of 0. So, this is like a quadratic equation in lambda square, and I can solve this quadratic equation and then I can compute it. So, that is what we will do right now. So, what I do is I multiply this equation by lambda to the power of 4 So, I get d11 pi 4 over lambda to the power of 4. So, what I am doing is I am reorganizing this entire equation. I am reorganizing this entire equation. So, this is plus 2 d12 plus 2 d66 pi to the power of 4 over lambda square b square plus d22 pi to the power of 4 over b square minus n pi square over lambda square is equal to 0. This is b to the power of 4. Okay. So, I delete pi square, this becomes pi square, this becomes pi square and this becomes pi square. And the other thing I do is I multiply this entire equation by lambda square. So, I get lambda to the power of 4. So, if I multiply the entire equation by lambda to the power of 4, this goes away and this goes away and this goes away, and instead what I have is lambda to the power of 2 here, lambda to the power of 4 here and lambda to the power of 2 here. Okay. So, I reorganize d11 pi square plus 2 d12 plus 2 d66 pi square minus n times lambda square plus d22 by b to the power of 4 times lambda to the power of 4 is equal to 0. And there is a b square here also. There is a b square here also. So, this is again a quadratic equation in what? It is in lambda square. So, from that we can compute value of lambda square. Okay. So, now we will consider the case, consider an isotropic plate and which is 1 meters in width. So, 1 meter wide. So, for an isotropic material we have shown earlier that d11 is equal to d22 is equal to d12 plus 2 d66 is equal to d. Okay. So, this equation becomes d times lambda to the power of 4 plus 2d, there is a pi square also here, times pi square minus n times lambda to the power of 2 plus d is equal to 0, right. So, there should be a pi square here also, there should be a pi square here also, and there should be a pi square here also. So, if I solve this, what do I get? Lambda square is equal to, so this is a quadratic equation and I can solve for it. So, it is, what is it, minus b plus minus b square minus 4ac divided by 2a. So, minus b, so this is b, so minus 2d pi square minus n plus minus b square minus 4ac. So, this is squared 2d pi square minus n whole thing square minus this times this. So, 4d square pi to the power of 4 divided by 2a. So, it is 2 pi square d. Okay. So, we will continue this. So, this is equal to minus 2d square minus n plus minus, what is this? So, this is 4d square pi 4 minus 4d pi square n minus n square or plus n square minus 4d square pi 4 divided by 2 pi square d. So, this term and this term they cancel out. So, this is equal to minus 2d square minus n plus minus n into n minus, and there is actually, I am sorry, I missed a pi square here. So, this is n minus 4d square, right, divided by 2 pi square d, yeah, pi square.
Starting also the 2d square pi square minus 10.
No, 1 second. So, this is minus 2d square pi square minus n, and this is n minus 4d pi square. d pi square. Okay. So, what does this tell us? If n is very small, so what is n? This is the plate, infinitely long, and I am applying n, and n is compressive. Okay. Now, if n becomes tensile, this number becomes negative and this number becomes negative, right. So, anyway, so point what I am trying to is, if n is very small, then the term under this thing will become negative. Suppose n is 0, then the term under the square root sign will be negative, and what that means is this entire thing, it will have an imaginary root. Okay. This will become only positive non-imaginary root only when n exceeds d pi square, 4d pi square, only n. So, the plate will start buckling only once n exceeds a certain number, okay, because otherwise the wavelength, which is lambda, it will be imaginary, because lambda square will be imaginary. So, lambda will also be imaginary. So, what this tells us is that Initially the plate will not buckle, but as I keep on increasing my external load, the plate after a certain point of time it will start buckling, and once it starts buckling it will develop its wavelength, and we can calculate the wavelength from this relation, and we will get two values for each value of n. So, we have to pick up the smaller value. So, that is there. And before buckling, what is the solution? Before buckling the solution is W naught equals 0, which we have seen here. So, before buckling this is the solution, W naught equals 0, the plate is flat, and after the plate buckles the wavelength corresponding to the n can be computed from this relationship. So, this is what I wanted to show today. Tomorrow we will continue this discussion. So, what we have discussed till so far is in context of infinitely long plates. Tomorrow we will see how we can use the same theory and same understanding in context of finite plates which are rectangular but of finite dimensions. So, that is pretty much it for today, and I look forward to seeing you tomorrow. Thank you.